Okay, hello class. Let's jump right into some of our derivations that we're going to be doing today, such as we're going to be talking about torque and lever arms and that kind of stuff. So let's define what torque is. Torque, we use the Greek letter tau, and this is defined by the force applied to a lever arm, FL. And what we can do is we can expand L into we can like break it up. And so what we'll do is we can then say that L is going to be equal to R sine phi, where phi is the angle in between the object. And so it's like, so if you say you have a wrench right around a bolt and you apply a force straight down, then sine phi is going to be all in the tangential direction here, where this is going to be 90 degrees. And then this is going to be just equal to R. But if you apply the force at an angle here, this angle is going to make sine phi less than just R. And so then you have to take an account for the angle. So when a force comes in at any certain angle, then you have to account for that extra angle there. So you can only write FR when sine is equal to 90, which is equal to 1. So that's the only time that you can write just FR in general. So at certain points, you're going to have to account for FR sine phi in this case. Now, for when the force is tangential, like we said before, when it's straight down like this, then we can say that this is F tan R, and that eliminates the sine phi. Or when you multiply F by sine phi, then you get the force that's tangential. So we can always expand this. This is the algebraic way to look at it, but now let's look at it like a vector. So now in this case, we're going to have torque as a vector, and so then T is going to be equal to R cross F. And so you can see that when you expand these two and you use the cross product of these two, you'll get that sine phi back out, and that's how we produce this. So algebraic, and then when we do this, this will be R FR sine phi. So that's how we get this formula here in the first place. So this is how we would usually start, and then we could go back and find this as our algebraic answer. Okay, so now we need to expand some of this torque formulation to talk about rigid bodies and angular acceleration. So we know that F1 tangential is going to be equal to M1 A1 tangential. But then we can, if we multiply both sides by R, we can have F1 tan R is equal to M1 R1 A1 tangential. And from there, what we can do is we can say, well, A1 tangential is just going to be A is equal to alpha R from our last chapter. And so then we can say that this is going to be M1 R1 squared alpha z. So it's the angular acceleration about the z-axis. So from here, we can do a couple things. One, we can instantly substitute in the torque on this side for T1. And then on this side, what we can do is we can go ahead and say that this is going to be I, or I1. And so then we can instantly say that for a general equation, that torque is going to be equal to the moment of inertia times the angular acceleration. So this is from an angular point of view. and the torques from what we derived before are going to be from a force point of view. So this is going to be the rotational analog for Newton's second law of a rigid body. So what's going to end up happening is we have to, in order to actually do this, we have to present this as a sum. So this is going to be the sum of torques over the sum of the bodies. So let's get these appropriate subscripts on there, and there you go. This is the rotational analog then for Newton's second law in a rotational body. So now I suggest that you do some of the examples out of your book. I think they will shed some more light on this kind of stuff. And I don't have the most amount of time. But so now we've gone from talking about torque as a general rotational force, but now we have to talk about energy with respect to rotation. So the kinetic energy for a rotating body, while it's moving also translationally, is the sum of the two. So we have treated kinetic energy as just rotational energy, and then just as translational energy, but now we have to put them back together. So then we can just sum up these two forces and say that K is going to be equal to 1/2 mVcm plus 1/2 ICM omega squared. So this is going to be a rigid body with both translational and rotational energy. So we can see that for certain objects that are going to be rotating, you're going to have a split between these two. And it's not going, so when you have an object rolling down a hill, all the energy is not going to be especially translational. It's not all going to be rotational energy. So they're going to have a split between the two. And so there are some things that we can do to manipulate this to talk about this. So one thing that we can do is we can say that VCM is going to be R omega. And from here, what we can do a couple things with R omega. We know that ICM has an R embedded in there, or an R squared embedded in there times the mass, and we can start to put these two equations together in order to form one rotational energy equation. So let's do that. So I feel like we did this briefly in the last chapter, but so VCM is going to be R omega, and so then that's going to yield 1/2 m R squared omega squared plus 1/2 I CM omega squared. And so then this is ICM here. And so then this is going to be equal to 1/2 ICM omega squared plus 1/2 ICM omega squared, and then that's just going to equal ICM omega squared, because you add the two halves together. So we can go ahead and we can add these up together in this way here. Okay, so next up we have to talk about work and power in rotational motion. So let's go ahead and derive some of the work equations for basic systems, and then from there we'll go on and talk about power. So for a disk that rotates through an infinitesimal angle d theta about a fixed axis during an infinitesimal time interval dt, the work done by this force is F tangential times that d theta. So then we can say that work is equal to theta 2, theta 1 here, and then we'll have tau z d theta. I'm going to rewrite that. And what we can do then is we can just say that once you do this integral, the tau z comes out because it's not dependent upon theta, and we can say that this is going to be equal to tau z delta theta. And we can do this a little more in depth by doing for the total work and talking about how this work can just be the difference in in rotational energy, and this will be kind of our rotational analog of the work energy theorem. So if what we're going to do is we say that work total is going to be equal to the integral from omega 1 to omega 2 of I omega z d omega z, then this is going to yield your work energy theorem for a rotational analog, because I is not going to be dependent upon omega. And then you just integrate for omega. That's going to give you a omega squared over 1/2. And then you just have to plug in omega 2 and omega 1. And that's basically the same thing as saying that the work is equal to the difference in the kinetic energy. So this is going to be rotational work is going to be equal to the difference in rotational kinetic energy. So this yields the same thing as we get 1/2 I omega 2 squared minus 1/2 I omega 1 squared. So it's basically the same thing. What about power? So if we go ahead and we say that the time derivative of the work is going to be equal to tau z d theta dt, because we're just taking the time derivative of both sides, then we can just say that P is equal to tau z over omega z. And this is your power equation for your rotational formula for power. Now we have to talk about angular momentum. So we're basically going to be we're going to be doing the same thing as we've done for the past 2 chapters, and we are going to be going ahead and saying that we are going to convert our translational equations into rotational equations. So we're going to have L, which is going to be our symbol for angular momentum, and that's going to be equal to R cross P. As we did the same thing for torque, we crossed F with R. And so then from here, we get that this is going to be R crossed MV. And so M is going to be a constant, so then it's just going to be R cross V, which in this case, in an algebraic sense, we get that L is equal to MV. R sine phi is just going to be equal to MVL. So L is going to be our lever arm, where our lever arm is just going to be R sine theta. So what we can do here is we can now find an analog between torque and angular momentum. And we can see that if we take the time derivative of L here, what we're going to get is we're going to end up getting R cross F, which is going to be equal to torque. So what we're doing is, again, if we take the time derivative here, it's going to carry through to the V here, and then you're going to get that's going to be the time derivative of V, and that's going to yield you the torque equation from before, and that's how we're going to get that's how we get torque here. So angular momentum for a rigid body, if we go ahead and we start talking about substituting in some of these equations here. So what we're going to do is we're going to say L is equal to MV R sine theta, like we did before, or sine phi, like we did before, and we say that V is equal to R omega, and then we're going to get that L is equal to M R squared omega sine phi. And this is how you usually do it. But if we're going to assume that all of this is tangential, we can just get rid of this, and then there you go. Now you have your equation for angular momentum, which in this case is going to be I omega, because that's what I is in there. So basically, we're just doing the same thing for our translational quantities as we are for the. We're just finding analogs for our rotational quantities from our translational quantities. So just remember this equation, the vectors here, if you're using this as a vector equation, go there for a rigid body rotating around a symmetry axis. And we also know that you just got to remember this equation here, where these two are equal. I'm not going to rewrite it again. But that's also another key equation that you're going to have to remember. So next thing that we have to get up is we talked about energy, we talked about momentum. Now we have to talk about conservation of that angular momentum. So again, we're finding a rotational analog for conservation of angular momentum here. And so then here we have to say with zero external net torque. So same thing with we were saying there's zero external net force. Now we're saying there's zero external net torque. We'll have the equations I1 omega 1 is equal to I2 omega 2. And this is going to be your base equation for conservation of angular momentum. We're going to have equations where we have that the torque of A on B is going to yield us. Sorry, let's see that we're. Yep, there we go. Is going to be dlb. This is a vector, so is this one over dt. And the same is true for the flip, or the opposite one, where we have tau b on A is going to be equal to dl A dt. So one thing that we should note is we talked about how when you pull your arms in, you gain angular momentum because of the parallel axis theorem. You can see this with the example that cats always fall on their feet. So if a cat is upside down, what it'll do it'll pull its arms inwards or its legs inwards to make it rotate faster, and then when it's ready to land, it'll extend them out, and then those legs will act as shock absorbers, increasing the amount of time that the cat has with the contact in the ground, and increasing, which gives it more time, which makes the impulse easier, which means it feels that force over a longer period of time, which then in turn reduces the impulse, which makes it feel less of that momentum change over a longer period of time. One thing that we can do here, going back to our equations, is when you add these two up, they should be equal to 0. So this is our big conservation statement, is that when you say that dlb dt plus dla dt, this is going to be equal to 0, which means that these two are the negatives of each other, which means that these two are going to be the negatives of each other. And so then we can say one last thing, that for 0 net internal torque, we can then say that dl dt as a whole is going to be equal to 0. So this is for the entire system here, and this is for parts of the system here, because this angular momentum has to be conserved. So one thing that we can do in this case is we can start using these differentials as and turn them into integral equations. So we can do the reverse as well. So what I mean by that is we can go ahead and say that dl is going to be equal to tau dt, or torque times an infinitesimal time interval. And you can go ahead and integrate this, and that will yield some some good insights into this problem. So what this part of the chapter is going to be talking about is we're going to be talking about gyroscopes and precession. This is 10.7 in this chapter. And what we're going to be doing is, if you go ahead and we're going to observe, we're going to introduce kind of a new quantity. So in this case, what we're going to be doing is we're going to be introducing omega, which is capital omega. The omega that we've been using before is the lowercase version of it. And this is going to be equal to d phi dt, which is going to be the rate at which the axis moves. And then this d phi here is going to be equal to dl over L. And these are magnitudes here. So we put absolute value signs around them. And so then we're going to have this over dt. And so what we can do here is we can go ahead and say that dl dt is going to be our torque. And so then that's going to yield us tau z over lz, which is going to yield us wr over iw. So what we've been doing here, yes, I can confirm that this here is going to be this is a W, not an omega here. This is going to be found in your book. Go ahead and definitely look at 10.7, because I don't think I'm explaining it well enough to do so. But this is your equation for, or your algebraic equation for precession. And I think now that I'm going to do some of the examples now that I've gone through most of the chapter. Okay, class. So for this first example, we're going to be calculating angular velocity. So what we're going to have here is, from the first example, we're going to have theta is equal to 2.0 radians per second, or radians per second cubed, and this is going to be multiplied by t cubed. So what we're going to be doing is they're giving us an expression for theta in this case, and what we can do here is we can find theta in radians, or what we're going to do here is we're going to solve the example, obviously, but we're going to show you how you can use derivative calculus in order to find different quantities from this one expression. So if we go ahead and just take the time derivative here, we're going to get that omega is going to be equal to d theta dt, and so then we're just going to get 3 times 2.0 radians per second cubed times t squared. And if you want to go ahead and do this again to get alpha, you'll just get that this is going to be equal to 6 times 2.0 radians per second cubed times t. And so we've easily just gone ahead and taken these two derivatives and gone ahead and found these three quantities for the system. So we want to find in radians and in degrees at t1 equals 2 seconds, and find it in t2 is equal to 5 seconds. So for this, all we have to do is we can go ahead and just plug in the seconds, or the time in seconds, into this equation up here, and that will yield us our answers for theta. And then on top of that, we just say, all right, well, now we have to find the distance that a particle on the flywheel moves over time interval from t1 equals 2 seconds to t2 is equal to 5 seconds. And so what we can do here is we just have to take the value at 5 that we got earlier and the value at 2, and we just subtract those two. And from there, we just multiply by the radius of said flywheel, and that will yield us your distance over the flywheel. And now we want to find the average angular velocity in radians per second and revolutions per minute. We're just going to do radians per second over that interval. And so what we can do here is finding the average angular velocity. We just have to go ahead and plug in those values for 5 and 2, and then subtract those said values. So all we have to do is we're going to plug in t into those equations again. We've already done that, so we already have these values in radians. And then you go ahead and you divide that by the time interval, which is going to be 3 seconds in this case. And then you just convert that answer from radians per second to revolutions per minute. And then here's the good one though. Find the instantaneous angular velocities at t1 equals 2 seconds and t1 is equal to 3, or t2 is equal to 5 seconds. So now in this case we do actually have to take the derivative, and so we've already done that. And now all we have to do is find the instantaneous angular velocities at t1 and t2. And so we can do that just by, we've already taken our derivative, so we just need to plug in t into this case as well. And so we plug in 5 seconds and 2 seconds here, and those will yield both of our instantaneous angular velocities. Okay, so next up we have calculating angular acceleration. And it's the same, it's using for the flywheel of example 9.1, so we've already got this already found out, or we've already taken the derivatives here. We go ahead and find the average angular acceleration between t1 and t2. So in this case, you just have to use the formula omega2 minus omega1 over t2 minus t1. And this is just the rotational analog of your average acceleration formula that we used in the first 2 chapters. And so then this will yield your average. And then finding your instantaneous, we want to use our time derivative here that we've already taken, and we plug in 5 and 2 seconds into the t slot, and those will yield our accelerations at those 2 points. And this example is easy peasy. You just start plugging in your numbers. So then if we go ahead and head over to example 9.3, we will have to, I don't think this example carries over. So the example reads as, you have finished watching a movie on Blu-ray and the disc is slowing to a stop. The disc angular velocity at time equals 0. So this is before it starts to slow down, or before this is when the angular acceleration is still equal to 0. So it's not slowing down or speeding up. So at this case, we have that omega is going to be equal to 27.5 radians per second. And this is at t equals 0. And then its angular acceleration is a constant, so now it's starting to decelerate. And so then we can say that alpha is equal to negative 10.0 radians per second squared. And now we have a line PQ on the disk surface lies along the x-axis at t equals 0. What is the disk angular velocity at t equals 0.3 seconds? What angle does PQ make with the x-axis at this time? So this is saying that we have our disk, right? And at t equals 0, we have this line through the x-axis. And they want to know from this point, where does this line here, what angle does it make with the x-axis after these 0.3 seconds? So what we can do is we have this constant angular acceleration here. And so in order to do that, or in order to find omega, we know that omega here is going to be equal to alpha t plus omega naught. And so what we can do here is we can multiply our alpha by our t, which is going to be 0.3 seconds. And we can, this is going to provide a negative value here that we have to subtract off from omega naught, and that will give us our new angular velocity at that certain time. And so then afterwards, it's going to ask us what angle does the line PQ make with the axis at this time. So it's going to have rotated, the disk is going to be rotated at 0.3 seconds. And so we have to find where this disk is after 0.3 seconds, or how far it is rotated. And so we can do that by using our one equation here, where theta is equal to 1/2 at squared plus omega naught t plus theta naught. And theta naught in this case, we're going to take the x-axis as the original position, so we can say that that's equal to 0. And so then this is going to yield our equation here. And so we can go ahead and plug these numbers in. And so we're going to plug this in to omega naught, and then we're going to plug in T1 is equal to 0.3 seconds. And we plug that in there. We'll plug that in here. We'll plug alpha in here and here, T in here, omega naught in here, and omega naught in here. And this will go ahead and yield your how far this has displaced, and it will yield your answer here for how far it's slowed down. And it turns out that we have it slows down by 3 radians per second for this answer, and it makes 1.24 revolutions here. So these are just the 2 equations that you would have to know here. So moving on to the next example, we're going to have an example where we're going to be throwing a discus here. And at this point in the chapter, we really haven't done anything new here. So we say that the athlete's arm is going to be 80 centimeters from its axis of rotation. So I'm going to just put that into meters just to stay consistent. So we're going to have 0.08 meters here as our radius. And the athlete is rotating at 10 radians per second. And this is at a certain instant. And the angular speed is increasing at 50 radians per second squared. So we can say that alpha is equal to 50 radians per second squared. And we can say that omega at this one instant is going to be 10.0 radians per second. So at this instant, we're finding the tangential and centripetal components of the acceleration of the discus and the magnitude of that acceleration. So this is going to be pretty easy to figure out, because we know that A tan is just going to be equal to R omega, or R alpha. And so then we just have to plug in what R is and alpha is, and that will yield our answer. And then we have to do that R radial is going to be omega squared R. So we just plug in omega, plug in R, and that will yield that. And then in order to put these 2 components together to find the actual acceleration, we're going to have to draw this out real quick. So if looking from the top down, because we know the discus is moving horizontally. So from the top down, say we have this circle. This is the path that the discus takes, and this is the arm here, and this is the discus here. So at this point, we have that A tangential is going to be in this direction, and that A radial is going to be in this direction. These 2 vectors make right angles with each other, so we can use Pythagorean theorem to find the actual acceleration vector, which will point somewhere in this direction, which makes sense because he's rotating like this. So in this case, what we can do is we're going to go ahead and just use Pythagorean theorem, which is going to state that A is equal to A tan squared plus A radial squared. And so we just square these 2 components, and we're going to get that we have R squared alpha squared plus omega to the 4th R squared. So then this is just going to be equal to this is going to be equal to r square root of alpha squared plus omega to the fourth. And this will yield RA here, algebraically. So now they just have you, and then you can just start plugging in your quantities here, and this comes out pretty simply. So next up, we have an example of designing a propeller. So you're designing an airplane propeller that is to turn at 2,400 RPMs. The forward speed of the plane is to be 50 meters per second. The speed of the tips of the propeller blades through the air must not exceed 270 meters per second. This is about 80% of the speed of sound in air. If the speed of the propeller tips are greater then they would produce a lot of noise. What is the maximum propeller radius? With this radius, what is the acceleration of the propeller tip? Okay, so first thing that they go ahead and do is they convert our omega into radians per second, which you guys should know how to do this this RPM to radians per second conversion by now, where we have omega is going to be equal to 251 radians per second. And so all you have to do here is you have to take 2,400 and you multiply it by 2 pi radians for one revolution. And then you have to divide your quantity by 60 seconds in order to get it in radians per second instead of revolutions per minute. Okay, so here we have to use Pythagorean theorem in order to solve this problem. And so we get that v tip here is going to be equal to the v of the plane squared plus v tangential. And so v tangential just comes out to be, we can just substitute in r omega here, and that will give us r squared omega squared. And from here we can go ahead and just solve for r. So what we're trying to do is we're trying to find what is the maximum propeller radius that will yield us this. So then we get that v tip squared minus v plane squared all over omega squared. And so we already have what omega is, and I believe that we're given the what we want the forward airspeed of the plane is, and we say that we want the tip speed to be less than this. Oh, and remember this is r squared. So when we take the square root, we get r is equal to the square root of v tip squared minus v plane squared. I wish I could write. All over omega. And omega just comes out of the square root because it's being divided by it. So we get that, all right, so if v tip is supposed to be 270 meters per second, the maximum propeller radius is going to be then, it's going to be like about 1.03 meters. And then what is the max? And then it says with this radius, what is the acceleration of the propeller tip? So what we can do here is, in order to find this, then we just say that a radial here is going to be equal to omega squared r. And so then you plug in what omega is and you plug in what you got for r, and then they just go ahead and they give you the radial acceleration here in both meters per second and g. And this propeller is producing a lot of g's in this case with 6,600. Okay, so now we're going to move on to example 9.6 here. And this is moment of inertias for different masses. Yeah, we've done everything so far. Okay, good. All right, so in this case now, we have a machine part that consists of 3 discs linked by lightweight struts. What is the body's moment of inertia about an axis through the center of disc A, perpendicular to the plane in the diagram? What is the moment of inertia about an axis through the centers of discs B and C? What is the body's kinetic energy if it rotates around the axis through A with angular speed omega? So we'll go through the identify and setup here. So first, let's address the first problem. For A, we're doing what is the body's moment of inertia about an axis to the center of disc A, perpendicular to the plane of the diagram. So in this case, we have our diagram is going to look like this. This is going to be A with mass MA. And then we'll have this bar here connecting to, so this disc is going to be vertical. So the axis of rotation is here. And so this is going to be, vertical. So it's going to rotate like this. But if you have this guy here, this is going to rotate like this. So this is going to be flatly produced. So I'm going to draw this a little bit better here. So this is going to be one circle, another circle. So this is going to be a cylinder that looks like this. And it's going to have another rod here, and this is going to be another cylinder that looks like this. And this is going to be a cylinder, but just turned 90 degrees. And these are also connected here. So this is going to be a 3, 4, 5 triangle, where this is going to be 0.3, this is going to be 0.4, and this is going to be 0.5. These are all going to be in meters. So what we can do is that gives us a certain amount of symmetry. Remember that this is a right angle here. And so first thing that we want to do is so we've set up the problem now. And so this is going to be the axis that goes through these two, and then this axis is going to come out of the board, in which this one will rotate. So this is going to be like this. And I'm trying my best here to draw this correctly. So what we're going to do is we're trying to find the moment of inertia as it's rotating through about the center of disc A. So this is going to be our origin here. And these two are going to be using the parallel axis theorem. So since this is located at the origin, this mass here, this is going to be irrelevant. And so we just have to use the parallel axis theorem with these two guys on the other sides here. So then in this case, we're going to have that that I of A is going to be equal to these two, and so then we're going to have sigma m r squared, and so then of I and I, this is going to be mc, and this is going to be mb. This will equal 0.1 kilograms. This will be equal to 0.2 kilograms. And this one's equal to 0.3 kilograms. Okay, so then we have, this is going to be, let's do MB first, and then RB squared plus MC plus RC squared. And so then we can just start going ahead and plugging in these values here. So for MC, we plug in 0.4 here, and then 0.2 here. And then for this one, we'll have 0.1 here, and then 0.5 here. And so then that will just yield your moment of inertia here, just by way of plugging things in. So then B asks, what is the moment of inertia about the axis through the centers of disc B and C? These two are now going to be R is equal to 0, and then A is the only one that matters. And so this distance here is going to be the distance from the axis that A rotates from. And so this distance here is going to be irrelevant. So then we just use the same theorem, and we say that IBC is going to be equal to MA/RA squared, in which case RA is going to be equal to RC, and then this will just yield your moment of inertia for IBC. And so then it's going to ask for the kinetic energy as it rotates through axis A with omega I. So we just take our this is going to be Ka is going to be equal to Ia times omega. So we just take our Ia that we found here and we multiply it by omega squared and then divide by 2, and this will yield your kinetic energy here. And so then this is 1/2, like this. And then you just start plugging in your quantities, and that will yield your answer. Okay, so next up we have example 9.7, which is going to be an unwinding cable. And so we wrap a light non-stretching cable around a solid cylinder of mass of 50 kilograms and a diameter of 0.12 meters, which rotates in a frictionless bearings and frictionless bearings at a stationary horizontal axis. We pull the free end of the cable with a constant 9 Newton force over a distance of 2 meters, and it turns the cylinder as it unwinds without slipping. In the cylinder is initially at rest. Find its final angular speed and the final speed of the cable. Okay, so we have our disc here, and this is going to have a mass of about 50 kilograms, and this is going to be put down here on this flat ground. The distance from here to the cable is going to be 0.12 meters, and then it's going to be pulled in this direction over 2 meters, and then the force here is going to be equal to 9.0 newtons. Okay, so we've outlined all the quantities here, and so then we have to say that that the work done in the cylinder is going to be equal to F times the amount that it's displaced. So then W is just going to be equal to 9 times 2, which is going to give us 18 here. This is going to be 18 joules. And so then we find the moment of inertia of our disk here. And so then we have that I is equal to 1/2 mr squared here because it's a disk. And we're just not using these axis theorems. So we plug in what M is, and we plug in what R is, and R is just going to be half of this. And so that's going to give us 50 times 0.06 squared divided by 2. And that will give you your moment of inertia. And so then we have to say that that K1 is equal to U1 plus our work equals K2 plus U2. So originally it's at rest and it doesn't have any potential energy, so both the potential energies cancel out, and so then we just get that the work done is going to be equal to the final kinetic energy. And so then we know that our work is going to be 18 joules, and we know that our kinetic energy is going to be equal to 1/2 I omega squared. So we've already found what I is as a algebraic quantity, and so we just then have to solve for omega, which is the speed at which this guy unwinds at. And from there we can multiply by the radius of the disk, and then we can find the cable speed. So in order to find omega, we have to say that W is going to be equal to 1/2. I'm just going to write out what I just said, basically. It's going to be equal to omega squared, and so omega is going to be equal to the square root of 2W over I. We multiply I to the other, we multiply 2 to the other side, divide by I, take the square root. And from there, you plug in 18 here, and you plug in what we found for I via this equation here into this equation here. And if you really, really wanted to make this, take this through all the way algebraically, we can say 2W over 1/2 mr squared here. And from there we get that W is going to be equal to 4 omega, or omega is going to be equal to 4W. I'm trying to make this as clear as possible. Over m r squared. This is going to be the square root here. So then you can simplify this even further. You can say 2 over r times the square root of W over m. And this will yield your angular velocity here. And then you just have to, in order to get what V is, you take V is equal to R omega. And so then when we plug that in, we'll get R times 2 over R W over M. And so then this is going to be equal to 2 square root of W over M. And there you go. That is going to be your cable speed. Okay, so I'm going to save the rest of the examples for you guys to do yourself, and I'm going to go over homework in the next video.